Hello and welcome to Computer Graphics using Autodesk Maya and the Unity engine. This is it, the math review. So get ready. I promise not to make this too horrible. We're just going to lightly go over vector topics such as addition, subtraction, the kinds of multiplication. We're also going to look at matrix transforms and how they work. Now, a lot of the material you're going to see here comes from the text Mathematics for Computer Graphics 3rd edition. This is an amazing reference. I recommend everyone pick it up. I use it all the time when I can't remember a particular concept. So, real objects, in reality, they have a volume, they have an interior, an exterior, right? So here's a treasure chest on the far right. That's a photo of a real object. We open it up and inside is treasure. But in computer graphics, well, we cheat a lot. We are only interested in what is visible, what can be seen by the user, how it looks. Does it look the way it's supposed to, even if we're not, necessarily simulating it properly? Does it perform the minimum amount of functionality we expect? Maybe we never anticipate the user opening this treasure chest, so why should I even make it animated or openable? We try to simplify things as much as possible, okay? So if we take a look here, we open up our treasure chest. I was lazy inside of Maya, and I never even bothered to model the interior. We already mentioned this in the introduction material, but objects are composed of collections of points, vertices, all right? So here we have V1, vector 1 has an X and a Y and a Z component. That's what makes it three-dimensional. Typically, these are stored as floating point values. Inside of Unity, they're vec3 objects. Now, for this math to make sense, for the computer to make sense of what we're trying to tell it, basically, we need to create a system that allows our static points, our static XYZ coordinates, to become dynamic and animatable, to move them around, right? Because remember, we have to translate, rotate, and scale things. To add two vectors, right? Visually, that's just taking one vector, taking the tail of the other one and placing it at the head, as you can see here. So here's vector 1 and vector 2. I've taken vector 2 and placed the tail at the head of vector 1, and then the addition of those two vectors is this new green vector right here. All you're doing is adding it component by component. The X terms add, the Y terms add, and the Z terms add together. The same process happens with subtraction. So with subtraction, you're actually you're inverting the second vector. So here's V1 and here's V2. Now we're taking V2 and placing it at the head of V1, but we're flipping the directionality. And this makes sense. If you negate a vector, if you multiply it by -1, you're actually creating a vector that's perfectly anti-parallel to that one. That is, it's same magnitude, but it faces a different direction. And this is also same thing as before, X minus X, Y minus Y, Z minus Z to make our final outcome, which is X prime, Y prime, and Z prime in this case. Subtraction is incredibly useful. It's a great way of determining how far you have to go to get to a new target. Multiplication by a scalar. This one's real easy, okay? This is the easiest kind of multiplication you can have with vectors, unfortunately. But the idea is you have a scalar value like 2 or 3 or 4 or 5 or whatever you want to, or 3.14159. Doesn't matter what that value is, okay? You're going to multiply each component by it. The important thing to understand is that this changes only the magnitude, that is how long the vector is. It does not change direction. Well, that's not true. If you multiply by a negative value, you're inverting the direction, okay? That's the only time it comes into play. Otherwise, if they're positive values, it's not changing the direction, just the magnitude. So here we have our X, Y, and Z values. We multiply that by a scalar, let's say 2, because we want to make it twice as long. X prime, Y prime, and Z prime are now going to be 2 times the X, 2 times the Y, and 2 times the Z. Simple, easy. This is used all the time when you want to do things like velocity or speed. That is, you determine the direction you want to move into, which is usually a unit vector, which is size 1, and then your object or the character has a certain speed they move at. And you multiply that unit vector by the speed to tell you how far you'd be able to travel in that time increment. And very important thing to be able to do with vectors is to determine the magnitude, or how large it is, the length of that vector, all right? And this is just the Pythagorean theorem extended to 3 dimensions. So it's the X value times itself, plus the Y value times itself, plus the Z value times itself. And then you take the square root of all of that to determine the magnitude of the vector. Now, once you get the magnitude, you can use this in a number of different ways, but one of the most important ways is to create a unit vector. If you take the original vector values and divide them by that magnitude, we like to take the magnitude in order to create unit vectors. And a unit vector means it has a length of 1. in many of our operations, we use unit vectors because it simplifies the math. We don't have to deal with these, a different sized object. Typically, when your vectors have all different lengths and they're not of length 1, you have to do some division to get rid of, to normalize them all to the same length. So let's try an example. What we're going to do here is add two vectors together to show off vector addition. In this example, we're only going to use a two-dimensional vector. So that's going to have an x and a y term. We're going to have two vectors. We're going to have vector 1, which is going to be equal to 1, 0. And we're going to have vector 2, which is going to be equal to 0, 1. So what that's going to look like on our coordinate system is this. Now when adding these vectors together, it's as simple as taking vector 1, drawing it out, taking vector 2, putting the tail of vector 2 on the head of vector 1, and of course the addition of these two will produce a third vector, vector 3 in this case. Alright? Well, let's look at the math behind this instead of just the geometry. So let's do vector 3 is equal to vector 2 plus vector 1, which is going to look like this. The x term and the y term, which I'm going to call x prime and y prime to differentiate them, is going to look like the following. X and y from V1 combined with the x and y of V2. Alright? We're going to combine like terms. That is, the x's combine and the y's combine. So the end is going to be x1 and y1 simply going to be equal to the value of x, value of y, plus this x and this y. So what we end up with is we take these terms and place them in here. So the x here is 1. So what this ends up becoming is the value of 1 plus 0. The value here, this y, is a value of 0. That becomes 0. This y was a 1. So let's place a 1 there. So our final outcome, x prime, y prime, is going to be equal to 1 plus 0, which is 1, 0 plus 1, which is 1. 1, 1. What's important to understand here is that this is not a unit circle. We have added two vectors together, both unit size, that is a vector of size 1, another vector of size 1, but we have received a new vector that is actually beyond a unit vector. So that's our new vector, vector 3. And how do I know this? Because you actually go ahead and make a circle connecting these two elements, you'll notice that this vector points beyond it. So that means we need to normalize these components. So our vector, vector 3, is equal to 1, 1. To normalize this, we need to know the magnitude. That is, we need to take the magnitude of vector 3. The way we're going to do this is very simple. We're going to take the square root of the x term squared summed with the y term squared. Of course, by squaring the term, what happens is we're getting rid of any negative values. Okay? And then when we sum these two and take the square root, we end up with just the length of that vector. So in our case, the magnitude is going to equal 1 squared plus 1 squared square root, which means the magnitude of vector 3 is going to be equal to 1 plus 1, which is 2, which is equal to the square root of 2. So now if we wish to normalize this, all we have to do is take vector 3, and if we want to, we can divide each component by this magnitude right here. Alright? So that is 1 divided by the square root of 2, and then 1 divided by the square root of 2. If you plot this value, what you'll end up with is the fact that this value lies exactly along the unit circle between the 2 points at a 45-degree angle. So that's how you add 2 vectors together. Now subtraction is just as easy as addition. I always like to use the example of an enemy trying to find the player when I talk about subtraction. So let's assume we have player 1 right there, and let's assume we have enemy 1 right there. What we want to do is figure out how to tell the enemy to move towards the player. We want to find out this vector, which I'm going to call D1. To do that, all we have to do is take the player's position, P1, subtract E1 from it, and that's going to give us D1, or the direction to move into. All right? So, all we need to do is take the components. So we're going to assume the same components from before. This is 1, 0, and this is going to be 0, 1. All right? So let's put those values in. Remember, we're dealing with the x on the top and the y values on the bottom. So for P1, our x value is 0, and our y value is going to be 1. In this case, 1. For E1, our x value is 1, and our y value is 0. Subtract, subtract, equals, equals. So 0 minus 1 is equal to negative 1. 1 minus 0 is, of course, equal to 1. And this becomes our vector. That is equal to D1. This is the direction we want to move towards to get from E1 to P1. So you use the magnitude to transform this vector from this size down to, what would this be? 1 over the square root of 2, and then of course 1 over the square root of 2. And that's our unit vector form. Now that we have this, usually just to give you an idea and to show you off another kind of vector operation, we'll multiply this by a scalar value. And that value is going to be our speed. All right, so our enemy has a speed, right? Let's just say that speed is, let's say he moves 0.5 meters per second. If we take that unit vector, if we take the unit vector and multiply that by this scalar 0.5, that's, and then of course we also have to multiply this by time, dot delta time in unity, which is the amount of time that's passed since our last update, we end up with the answer of how much to move the enemy. And so this is a very good example of why vector subtraction, using the magnitude, and of course then doing a scalar operation on that vector to decrease or increase its size, its magnitude, is very important for figuring out how to move objects around in the 3D world. So far, we've taken a look at the theory behind simple vector operations such as addition, subtraction, scalar multiplication, taking the magnitude as well as converting that over into a unit vector. And then we did a few worked examples on paper. Now we're going to see how we can use vectors within Unity. So the first thing I've done is I just loaded up a scene. It has a couple assets that are already been created. I made these for a different project for dinosaurs. Here's a horsetail plant and a lilac flower. For you, though, you're probably just going to want to go to Game Object, 3D Objects, and create maybe a simple cube and a sphere. The intent behind this is I'm going to make this horribly aggressive horsetail plant chase after this peaceful lilac bush. And we're going to use simple vector subtraction to determine the distance between these two objects, or that is the direction and distance between these two objects, and then of course moving this lilac slowly towards it over time. So the first thing we need to do is to create a script. Go ahead somewhere in your assets folder, right click and create a C# script. I'm going to call this enemy seek. I'm going to double click and this will either launch MonoDevelop or Visual Studio depending upon what you've set up for your particular install of Unity. Now in this case I don't need to do a whole lot with start. All I need to do is set up a few parameters. The first thing I need to do is I need to know where I'm moving towards. I need my target. To do that, I want to store a transform. So let's do public transform, and let's call this target. The next thing I need to do is make sure I know the speed that I can move at, my maximum speed. So I'm going to create a floating value, public float max speed. Because these are public, I have access to these within the editor. But first I need to add this script to one of my game objects. I'm going to grab my horsetail and of course click and drag my enemy seek script on top of it. Now I have two input areas in my inspector to add items. The first is a target, which takes a type transform. I'm going to lock my inspector, click on my lilac bush. By locking the inspector, I don't have to worry about it showing me information about the lilac plant. Now I can click and drag the lilac over to this location, and it will automatically store the transform. It'll store a reference to the lilac's transform in this object. Next up is max speed. Right now it's set to 0. Let's set that to something a little bit more reasonable, maybe 2.0 meters per second. Now that we've set that up, let's go back to our script. There's only one thing we really need to do, and that is subtract the target from our current location. So I want to move towards my target. So I need to do a vector 3. Let's call this difference is equal to my target minus, target.position. The transform itself does not hold the position and only the position. It also has rotational information and quite a few functions. So first you need to specify the position, then you need to subtract our position. We get this object's position by calling GameObject.transform.position. All right, so this should then calculate the difference between the horsetail's location and the lilac plant's location. However, remember that is the full distance between these two objects. I don't want to move that far. I don't want to instantly teleport to my final location. I want this object to slowly move towards it based upon our update rate. Therefore, I need to make sure I normalize this vector. Let's do difference is equal to difference dot. And there's two normalized functions in Unity. There's normalized, which returns the vector of that type of size 1, or there's the normalize function, which makes this particular vector into a unit of value 1. So what I want right now is normalized. I also want to make sure, though, that I multiply this by my max speed. I still have a time value in my units. I need to get rid of that. To get rid of it, I multiply by time.delta time. So based upon how much time has passed, how fast I'm allowed to move, and of course this unit vector which holds my distance, I can then determine how much I should move. Now I just need to update my position with that amount. So let's do GameObject.transform.position plus equals difference. And that's it. That's all I need to be able to continually update this object. As each update phase happens, a small amount of time passes, I move a little bit based upon my maximum speed, and I update my location accordingly. So now I should be able to just hit the run button and watch as my lilac plant is continually chased by this horribly aggressive horsetail. And that's really it for this lesson. Hopefully you've gained a better understanding of vectors, how to do things on paper, and of course also how to implement simple things inside of Unity. I mean, this is incredibly simple, but it's very powerful. You can make incredibly simple games that are fun to play just by having these enemies continually seek this location. Remember, if you found any of this interesting or you want more content, please like and of course subscribe. In addition, if you didn't like something or you want further explanation, make sure you comment below. Thank you.